Namaste and welcome to this open session. This talk is called From Doubt to Devotion, a tale of falling in love with automated testing. A little bit about me. My name is Siddharth Mishra and I'm a programmer from Sumo, India. And as you can see, I'm a big Potterhead, so I expect a big and loud virtual cheer from all of the Potterheads watching this talk. Thank you. Alright, I have divided this presentation into three separate sections. The first is why you should do automated testing. The second is what is automated testing. And the third is how you can do automated testing in games. I have a confession to make. When I conceived the idea of this talk, I was already convinced that we should do automated testing in games. And I was going to talk about my journey concerning the how to do it part of becoming sure that you can do automated testing in games. However, I very quickly realized that to delve into the how to do it part, you first need the incentive of understanding the desperate need of having automated tests in games. And hence, I've slightly pivoted this presentation to talk more about the need of automated testing in games and a little less about how to do it. However, we still do touch a tad bit on the how part, but I do hope to get into greater details of that in subsequent or sequel presentations of this talk. Alright, with that out of the way, let's begin. As you all know, this is a talk about falling in love. And the why part of falling in love is often the most important bit. So, why do you love me? Asks automated tests. The why. Here's what I've personally observed about the games industry. I believe you might relate to some of this. In our industry, months of bug fixing is normalized. Months of changing an existing code base to forcefully reuse legacy code for a sequel might not get frowned upon as an idea. Coming back from holiday and seeing code you wrote malfunctioning because someone else changed it, or they worked on something else but they indirectly changed how your feature was working, is considered part of the process. We don't really embrace change, do we? Is that all? Unfortunately not. Refactoring is almost impossible because you don't really know if you're breaking something when you're refactoring code. So you never know if it is productive. Code bases are harder to navigate for folks with less application domain knowledge, which is anybody who's either new to the project or new to the industry. There's no way for art to verify the validity of assets until a build is created. Fixing one bug might open another, and I heard this interesting stat that this happens 30% of times, as high as that. Adding new functionality takes more time with passing time. QA teams spend more time reporting trivial bugs. Anything non-visual is impossible to test. And all of that leads to decreased player satisfaction, and also to the developmental costs of games is spiraling up, and that is almost becoming a very problematic thing, and this is completely non-sustainable. So what is it that I found in my journey that can fix almost all of this? What can shorten the feedback loop where a bug can be found even before a build is made? What can make refactoring safe and software soft? What is it that I have fallen in love with? Drum rolls. Automated testing. Imagine confetti. Alright, so you'll see how automated testing fixes all of these issues that I mentioned, but first let's understand what automated testing is. So what is automated testing? Automated testing is the process of leveraging automated tests to validate the functionality and ensure it meets requirements before being released into production. It's in the name. When we say automated testing, we basically mean there's no manual intervention for running each test case. The major types of automated testing are end-to-end tests, integration tests, and unit tests. Let's take these one by one. What are end-to-end tests? Let's take an example of an open world game. So imagine an open world game where there's a spawn player that you can move around, there are cars that you can steal, guns you can fire, etc. An end-to-end test scenario could be defined as a user being able to move to their nearest car, sit and start driving the car. To write an end-to-end test for it, you'll have to do the following. Instantiate all of the state required for the player to be spawned, the car to be spawned, etc. So basically instantiating the environment. So basically the whole game. Um, Provide appropriate input is the second step to the player to perform the required actions at the appropriate time intervals. And the third step is to check whether the player was able to move, sit in the car, and start driving it or not. As we can see here, end-to-end tests simulate real user scenarios and interactions with the application's user interface and backend systems, including servers, including file systems, etc. These also do require a lot of dev effort to create and maintain, because you have to prepare all of this state that I just talked about inside of a test method, basically inside of a test. And these are very hard to maintain as well, because when any of that logic changes, this test is likely to change, because the scope of end-to-end test is so high, and we are going to give it 5 stars for that. And by scope, I do mean end-to-end tests cover a lot of the code base. So a single end-to-end test can cover multiple components and multiple backend systems, etc. Because of that, any small little change somewhere can break an end-to-end test. So you can't really be just happy with having end-to-end tests. As well as the precision of end-to-end tests is not as high. So when an end-to-end test fails, it tells you that something is wrong, and that is very important to know. But it's not precise, and by precise I mean that a test is more precise when it fails and it tells you exactly what is broken. End-to-end tests don't do that. The speed of end-to-end tests is also low, because they need all of this compilation, all of this runtime calculations, this state development that you need to be in this state. They take a lot of time to run and compile. So yeah, they are slow. All right, let's move on to integration tests. Back to the open world example. An integration test could be a test that tests the integration of different components of our system. So for an example, that could be the movement system and the input system. So an integration test can test whether the movement system is responding properly to the inputs given in the input system. And both of these systems are the real systems used by the game. And I'll get to what I mean by real in a bit when we talk about unit tests and how they mock dependencies. Integration tests ensure that these components work together correctly when integrated, and they also have multiple failure points. So in our example, even if the input system breaks, the test is going to break. If the movement system breaks, the test is going to break. And even if both of those work correctly but they don't integrate together properly, it's still going to break. So multiple failure points. The scope of integration tests is smaller, it is lesser than the end-to-end tests, because it covers multiple components only and not more than that. The precision is higher as compared to end-to-end tests, because again, if you're decreasing the scope, the precision is going to be high, and you're going to be able to tell with a little more confidence where the problem is if an integration test fail. The speed is also a tad bit higher as compared to end-to-end tests. Let's move on to unit tests. But before that, I want to talk about what a good unit test is. And the reason for that is a bad unit test could be an integration test. It could also be an end-to-end test. So to properly contrast all of these, you need to understand what a good unit test is. A good unit test is able to pinpoint the exact bug when it fails. It is fast, it is isolated, it is consistent and reliable, it is easy to implement, and it is relevant tomorrow. The scope of a good unit test is 1 star. It's not great. You don't cover a lot of the code base when you have a unit test. However, the precision of unit test is amazing. You have 5 stars of precision for good unit tests, because when a good unit test fails, the whole purpose of a good unit test failing is to tell you that this particular thing is broken in this particular system. So it tells you exactly where the bug is. And the speed of unit tests is higher. A good unit test is supposed to run in milliseconds, as fast as you can run a test. You're gonna run a unit test. All right, but what is a unit test? We'll first understand what a unit of work is. A unit of work is the sum of actions that take place between the invocation of a public method in the system and a single noticeable end result by a test of that system. Notice the words noticeable end result. By that I mean you shouldn't have to look into the internals or privates of a class to notice this end result. The pun is unintended, by the way. A noticeable end result could be any of the following. First, it could be the invoke public method returns a value. Second, it could be there's a noticeable change to the state or behavior of the system before and after the invocation that can be determined without interrogating the previous the private state. And third, there is a call out to another system over which the test has no control. That could also be a noticeable end result. We don't care about the value that this call out returns, so we are not going to assert against the value that returns, but we are just going to check if there is a call out or not. That is considered as a noticeable end result as well. Finally, we can define what unit testing is. A unit test is an automated piece of code that invokes the unit of work being tested, and then it checks some assumptions about a single noticeable end result of that unit. Let's try to compile all of that information together in the testing pyramid. The testing pyramid is a conceptual model that illustrates the ideal distribution of automated tests across different levels of granularity in software development. The bigger the volume of a section is, the more of those kind of tests you'd want to have in a game. But that begs the question, why? Why don't you want to have a single end-to-end test that runs throughout your game and just tests everything? Or why do you want to test a single unit of work when you can test real dependencies using integration tests? Why would you want to do any of that? And the answers are in the arrows. All right, so why do you want unit tests more than integration tests and integration tests more than end-to-end tests? First, faster feedback. Unit tests provide fast feedback during development, enabling developers to catch and fix bugs early in the developmental cycle. So you don't have to wait for a build. And unit tests are faster than integration tests. And integration tests are faster than end-to-end tests. So if you have them in this proportion, a developer is more likely to run them more often than other kinds of tests. Second is isolation of issues. Unit tests inherently isolate units of work. So they basically help isolate issues to specific units of code, making it easier to identify and fix problems. Third is lower maintenance overhead. Unit tests have low maintenance overhead compared to integration tests, and they have lower maintenance overhead compared to end-to-end tests, reducing the time and effort required to maintain the test suite. So you want all of those, but you want to have them in a proper proportion. To be clear, this implies that for each unit that you have, for each unit of work, you want to have at least a single unit test. If you can have more, then that is great because you can have multiple edge cases. A unit test will tell you about breaking of the individual logic of a unit. So if there's a bug in the unit of work, the unit test is going to tell you. If there's a bug in the integration of multiple units or components, an integration test is going to tell you. And if there's a bug in the peripheral systems or in the servers, in the environmental factors of a game, or basically anything, the end-to-end tests are going to be on your side. All right, that lends us into the third section. How to do automated testing, how to do unit testing, and especially inside of unit testing, how can you really separate dependencies at all? Because the last I checked, all games that we create are a beautiful concoction of multiple really beautiful systems all working together. So how can we do it? The answer is hidden in the stars. Flying people into space presents interesting challenges to engineers and astronauts. One of the more difficult being how to make sure the astronaut is ready to go into space and operate all the machinery during orbit. A full integration test, mind you, for the space shuttle would have required being in space, and that's obviously not a safe way to test astronauts, is it? That's why NASA built full simulators that mimic the surroundings of a space shuttle's control deck, which remove the external dependency of having to be in outer space. So how do rocket scientists do unit tests? There's a definite pattern if you can observe it for breaking dependencies. First, we find the interface or API that the object under test works against. The object under test in our example are the astronauts or their ability to handle equipment in space. The interface that they are working against are the joysticks and monitors of the space shuttle. Second, you replace the underlying implementation of the interfaces that these objects in a test are working against with something that you have more control over. So you want more control, so you replace the underlying implementation of this interface. This involved hooking up, for the space example, this involved hooking up various shuttle monitors, joysticks, and buttons to a control room where test engineers were able to control what the space shuttle interface was showing to the astronauts under test. Let's transfer this pattern to code. Let's say we have a log as a class which has a public bool method which returns a boolean called isValidFileName. It takes a file name string as a parameter, and so basically what it's supposed to do is to tell you if a file name is valid or not based on the extension of the file name. Now what this does in production code, assume that it goes to a file system and it reads through the configuration file stored on the file system, and then if the configuration file tells us that the file name extension is supported, it returns true, otherwise it returns false. So it basically encapsulates the logic necessary to validate file names against a set of predefined criteria which we have stored in the file system. To write a test for it, what we'll have to do is first we'll have to create the file system. We'll have to create a config file to allow for the required extensions. So in our example, we want the .exe extensions to be allowed. So we create a config file allowing that. We add this config file to the file system. We add the file system dependency to the login as a class. And then we run this method. We pass in the correct file name .ext and we expect it to return true. However, as you can see, there are a couple of problems with this because this is now looking like an integration test. Once this test depends on the file system, you're performing an integration test and you have all the associated problems with integration tests. Integration tests are slower to run, they need configuration, they test multiple things and so on. Don't get me wrong, integration tests are important, but you need, given by the test pyramid, you need more unit tests before you have integration tests. This, as an example, is the essence of test inhibiting design. The code has an external dependency on a resource which might break the test even though the code's logic is perfectly valid. So even if the unit under test is working perfectly, even if we can't get to the file system, maybe there's a server problem to get to the file system, or maybe the file system is corrupted, maybe it is not initialized, all of those scenarios will lead this test to break even though the logic of this unit of work is fine. So there's a direct dependence on the file system. And what we are going to do is we are going to use the space example, what we learned there, to refactor this. How will we refactor this? First, what we did there is to find the interface that the unit of work under test works against. By the way, in this case, interface isn't being used in the pure object-oriented sense. It just refers to the defined method or class being collaborated with. In our example, the interface is the file system configuration file. Second, what we need to do is that if the interface is directly connected to the unit of work under test, as in this case, you're calling directly into the file system, to make this code testable, we can add a level of indirection hiding this interface. So what we can do is we can move the direct call to the file system to a separate class, and you can see that in the file system, in the file extension manager, this is a separate class that we have added. There are a bunch of other ways to add indirection to your code and refactor your code to be refactor your design to be more testable, by the way. But in the interest of time, let's stick with this one. The third step and the final step is to replace the underlying implementation of this layer that we have added with something that you have more control over. So in this case, the instance of file extension manager, we don't really have control over it, but we can replace it with a stub class that we can have more control over. Let's look at what I'm trying to talk about. By the way, by a stub, I mean a controllable replacement for an existing dependency or a collaborator in the system. By using a stub, we can test the code without dealing with the dependency directly. So let's see what we have done here. Interesting interfaces. The method talks to the I extension manager, and so basically what we have done here is we have added an interface that the unit under test is dealing with, instead of directly dealing with the file extension manager, and by extension of that directly dealing with the file system. Now now that we have introduced this seam into our code, we can at test time let stub extension manager be the thing that the unit under test is talking to, instead of the file extension manager be the thing that the unit under test is talking to. Let's see what I'm talking about. But before that, I introduced an interface in here, right? How do we do that? That's the answer: dependency injection. So what we are basically doing is we are trying to set up ourselves to inject a fake implementation into a unit under test. There are several proven ways to create interface-based themes in your code. Places where you can inject an implementation of an interface into a class to be used in its methods. Some notable ways include receiving an interface at the constructor level, saving it in a field for later use, receiving an interface as a property getter set, receiving an interface just before the call in the method by doing any of the following: a parameter to the method, which is parameter injection, a factory class, a local factory method, or variations on the preceding techniques. What we are going to stick with is constructor dependency injection. So basically constructor injection. All right, so let's see how we can do constructor injection in our class as an example of dependency injection. We have introduced the seam in our class now in our production code as a field of type iExtensionManager. iExtensionManager is an interface which has a method isValid, which returns true or false based on the file name. Now we inject an instance of iExtensionManager in the constructor of this class, and then later save it in a field for later use. Now this login as a class will be called in two separate places with two different instances, and I'll tell you what those are. The first is going to be the real file extension manager being passed here. It will also extend this iExtension manager, but it will ultimately use the real file system. So it's actually going to do whatever it was supposed to do. So it's going to check in the config file, and it's going to use the file system to tell us if .ext is supported or not. However, the replacement of the real file extension manager is our fake file extension manager, which we are calling stub extension manager right here. It also extends iExtension manager, so it implements this isValid method, but it returns this will be valid field, which is publicly settable from anywhere. So this is basically a pawn. This is something that we have complete control over, which actually makes this a unit test. Finally, looking at the test code, we have the method, and the name of the method for this test is very important. For any test is very important. The name is, it reads isValid file name supported extension returns true. This is basically saying that we are testing isValid file name unit, and if the name is a supported extension, we should return true. In this test, we create an instance of the stub and we set it to return true. It will be valid. Now we create the login analyzer instance using the stub extension manager, and we inject the stub in here. see, this is a test code, is going to inject the stub because we don't want to depend on the file system. We want to uh, we want to remove the dependency from the file system and have more control over the situation. Finally, we assert true on the result of log answer dot is valid log file name, and we want it to return true because we are passing in an acceptable extension. So as we remember, the .ext extension was supposed to be an acceptable extension. So if we pass in the .ext extension, we want it to return true irrespective of what the file system is saying, because that is the functionality that is covered by this unit under work. This unit under work doesn't really care about the file system. All of this unit under work cares about is if the file name is valid or not, and that is what this actually is testing now when we are using the stub extension manager. All right, let's look at TOOD because that's what we have just achieved. TOOD is nothing but testable object oriented design. It's assuming that tests are just another player of your game. When you write unit tests for your code, you're adding another end user, the tests, to the object model, your application. The end user is just as important as the original one, but it has different goals when using the model. It does take extra work, but more often than not, there are solid benefits. Just to give you an example, the open close principle does talk about this. Your model should be open for extension but closed for modification. So having testable object oriented design has a lot of overlaps with having solid design. So you could basically say that this extra design were required for testability points out design issues that you hadn't considered and that you might have been expected to incorporate in your design anyway. However, testable design doesn't always mean good design. So this is just to say that let solid be your primary lens for designing your software, and then use testable object-oriented design principles to make your design testable enough so that you can test it properly. Ultimately, good design is good design, and you really want to keep solid very close to you. All right, so that makes us jump into the benefits of this whole presentation. Note that these are not benefits just to the code team, by the way, but also to the design, QA, production, art, and everyone else involved in making the game. We are going to look at all of the problems, by the way, I listed in the starting of this presentation, and we are going to see how automated testing fixes it. Months of bug fixing. Well, when you have automated tests, there are inherently going to be less bugs, and the bugs are going to be easier to find, and hence you can squash them. Months of changing an existing code base to forcefully reuse legacy code for a sequel. Well, that's not as big as a problem, because when you have tests for your code, it's not legacy code. It's code that you can really work with. And also, tests do act as documentation. So even if it is code that is written by someone else, you can refer to the test of that code and you can understand what was the intention of that functionality. Also, now refactoring is possible, because when you get immediate feedback when you're breaking someone else's code, or you're breaking even the code that you wrote 6 months back, you'll get immediate feedback when you break something with a code change. Third problem is code bases are harder to navigate for folks with less application domain knowledge. How automated testing fixes it? Well, tests act as documentation again. So someone who's new to the project, instead of having to skim through huge documentations, all they can just actually jump into code, run the tests, see the tests, and understand what the code base is supposed to be doing. Also, tests provide a safety net for someone who isn't sure about what they are doing. So if somebody is probably new to the project and they write some code that is problematic, they're going to get immediate feedback and they are not going to break the software. Design teams are not empowered to change design, and this is a tricky one. However, I am of the opinion that tests help us embrace change. When you have tests and let's say the design changes, the tests help ensure that when you are changing the functionality that changed, you're not breaking the functionality that stays constant. And also, especially in game development, I do believe that fun is iterative a lot of the times. So you are more than likely bound to change your design, and I think you should be empowered to change your design, and I think tests help you do that. Fourth problem, sorry, fifth problem is coming back from holiday and seeing code you wrote malfunctioning because someone has changed it. Well, that's not going to happen, because when you have fast unit tests, it makes it easy to run them ever so often. And when you run them after every little change, you get immediate feedback when you're breaking something. So forget about the bugs that come through that, and forget about breaking functionality of a colleague of yours. There are more. Fixing one bug opens another. Well, how do automated testing fixes it? Almost impossible with immediate feedback. When you have tests covering the area, let's say there's person X and person Y, uh, and when you fix a bug, when person X fixes a bug, if the person Y has tests for the functionality they created, even if the person X is breaking the code, breaking the logic in the person Y's code, they are going to immediately know as soon as they run the unit tests. So this is not going to happen. There is no way for R to verify validity of assets until a build is created. And this is an interesting one, because uh, testing is really for almost all of the whole game development team. With asset submission pipelines, you can really speed up the art processes, because they get immediate feedback on various aspects. I'll give you an example. Let's say there is a limit in your game. There's a processing limit that you want character meshes to be only of 5,000 polygons, and let's say building meshes of only 20,000 polygons. If you have a test for that in your asset submission pipeline, whenever an artist submits an asset, they're going to get immediate feedback without a build breaking, that either they have more space to use more polygons in their model, or they need to cut a couple of polygons, not a couple, maybe a little bit more of polygons from their asset. One of the most important questions is, won't this add more time to the project? And I believe that higher quality and maintainability facilitate faster, more reliable coding with fewer bugs and quicker bug fixes. There have been a lot of experiments inside of the game development industry and outside of the game development industry that prove this. And this is a technique that has been used in the industry, not just the game development industry, but other industries like the web industry, for literally tens of years. So there's really no excuse to not do this. And especially when you have, I'll just quickly mention TDD here. When you have TDD and you do test first, it just becomes, instead of using extra time to write the test, you're basically thinking about the functionality when you're writing the test. So you're basically defining the requirements of that piece of code that you are writing. So it's basically just planning. It's not extra time that you are taking. QA teams spend more time reporting trivial bugs. With tests, instead of finding boring bugs where every other click causes an exception of some sorts, the QA teams can concentrate on uncovering logical bugs in real scenarios. So they can really play the game for longer times because the bugs are less, and then they can, spend more time finding logical applicative bugs instead of reporting trivial bugs like, I open this screen and there's this exception, and because there was no unit test or there was no integration test to check if that screen is going to open fine or not, if the data is being passed properly or not. That is just I do think that QA teams, the time that they have, we can use it more wisely. Does this negatively impact the role of manual QA? Completely not. Unit testing enriches, in fact, the QA roles by offering a first line of defense against bugs, while QA ensures user acceptance. So the bugs are more than often handled by the tests that you have, and the QAs can ensure user acceptance. So they can ensure whether something is behaving properly or not, instead of finding bugs in that thing. That almost leads us to the end of this talk. And before we move to the QA, I just wanted to mention the references and inspirations for this talk. This talk is almost wholly based upon The Art of Unit Testing by Roy Shurov. So that and all of the awesome people on the screen right now, they deserve heartfelt mention from my side, because they have really helped me do this. I couldn't never have done this without reading all of these awesome books or talking to all of these awesome people. So yeah, uh, please do read these books, check out these different resources. I have more resources. We can talk about that later. And I also like to mention ATIG, the Discord group, which has this small community of automated testing in games. So a special shout out to them. All right. So thank you a lot for listening to this talk. I appreciate it a lot. You can find me on that LinkedIn QR code that I added, and this is time for QA now. So any questions?
Hello, everybody, and thank you for joining us today. Today, we are also joined by Siddharth, joining us from all the way over in Sumo, Pune. We've had a few questions pop in. I think we've got just under 10 minutes to go, so we'll just try and rattle through those as many of those as we can. So we've got the first one in Siddharth, which is from Theodore, which says, "What do we write first, the test or the code?"
Hello, everyone. Right, so this is a great question, and I do touch upon this in very brief. But to answer that, I do think that writing tests first, that is TDD, is a great way of writing tests. However, I'd like to mention that adapting automated testing in your project while adapting TDD is not an easy job. If you can do it, um, I mean that there couldn't be anything better. And I have examples that have done that and created games which are really awesome. So that's that. But again, I do think that writing tests first is great, but it's writing tests at all is better. Writing good tests at all is better than writing no tests, and uh, best is TDD.
Thank you. Okay, so the next one we've got in from Gary, and this is a bit of a mouthful, so apologies if I trip over my words. This says, automated testing and rapid prototyping of systems don't play well together as ideas, as you are guaranteed to have a lot of throwaway ideas and often short time windows to produce demos. Where do you see automated testing in this sort of rapid iterative scenario?
Yeah, so my answer to that would be twofold. However, that is a great question again. So the first thing is that I usually like to differentiate between types of projects. So if your project is running for more than 6 months, about a year, or anything more than that, I think you will benefit a lot from automated tests and unit tests. So, but yeah, if this is something that you are just prototyping, you're gonna work it for a couple months, just try out different functionalities. Uh, you can make that decision to drop automated testing from project to project based on the type of project. The other thing is that this is not to mean that writing automated tests slows you down. If you do TDD, it becomes just a design process. So when you are writing the test before writing the code, you are just designing what your code is supposed to do. And when you do that more often, when you have experience doing that, it stops slowing you down. In fact, it starts speeding you up. So if you have adapted to it as a process, then it doesn't slow you down even in prototyping. But I don't mind dropping automated tests in rapid prototyping phases. That's my
Cool.
answer.
Thanks, Siddharth. Okay, so the next one we have in is from Liam. It says, if you're on a project that's been ongoing for a while but isn't using unit testing, do you have any advice for how to approach adding it into the project?
Um, yeah, I do. And to be honest, that's one thing that's greatly covered in Roy Oshurov's The Art of Unit Testing, and that is how software companies can adapt to using automated testing. The thing is that it's tricky, and I have tried this in a couple of endeavors, and I believe that it needs support from the management. It needs support from the leads, and it's hard to do it from bottom up. It is not impossible, but I do believe that if you have support from top to bottom, that really helps it percolate, because it needs its own reservations to do it. However, to do it, firstly, you can go on and read the awesome references that I've done, and the second thing is to start adapting to it gradually, and uh, this is a whole topic of its own. Maybe we can connect separately, but yeah, I think the art of unit testing, yeah, it really covers this in real depth. So yeah, we can go about that separately, I guess.
Awesome. Thanks, Siddharth. We've got one here from Daniela, which says, at what point of a project should we start implementing automated testing?
uh, right at the moment you start write the first line of code.
Awesome. Short and sweet, that one. Cheers. Okay, we've got one in from Peter. It says, have you tried writing tests in Unreal? How are you handling mocking engine classes?
Yeah, and now that's an interesting one again. um, to answer you, I haven't tried writing tests in Unreal because most of my experience is concerning Unity. So I don't know about that, but I highly believe, and I've read documentation on this, that Unreal is not going to make a difference in the philosophy of automated testing. You can do it in Unity, you can do it in Unreal, because you can do it in everywhere, in every industry, in every everywhere you can write code. To answer your specific question about writing, dealing with engine code, I think it's important to understand that the engines, they are testing their own code. So if you use rider or the tools to understand, to decompile their engine code, you can see they have written lakhs of tests to test their own engine code. So you're testing your own logic. You need to uh, pick and choose and you don't want to be testing the engine code. One type of unit that you can test is when you are invoking a third party, that I mentioned in my talk. So even if you are invoking a third party call, you can write a test for that, and you can just check if I'm calling this thing from Unreal's code or not. You don't need to test if that thing outputs well or not, because that is Unreal. That's what Unreal needs to test. It's their code. So you can test if you're calling their code properly or not, and then you can just depend upon the third party assets or your engine working well.
Cool. Thank you. Okay, we'll try. We've got two left. We'll try and get through them both, but I'm going to go for this one from Gary first, and it says, in my experience, maintaining automated testing code coverage gets increasingly difficult over the life of a project, as it's often the first thing to be sacrificed when there is time pressure. Then, as a project matures post-release, it gets less code support, further making it difficult to reduce technical debt. I'm interested on your thoughts on this, as I think it's a common failure to implement automated testing.
Yeah, that is a big problem. So firstly, just trying to quickly answer that, I'll try my best. First thing is that code coverage is again a stat, and as you try to increase or maintain stats, people find ways to trick them. So I don't really like talking about code coverages and things like that. I think they are easy to confuse such sets. However, that question stands on its own, that automated testing for larger projects becomes difficult. But I think that with the right techniques and with the right approaches, it's not impossible. And it's really difficult, but the pros outweigh the cons. So the difficulty, the extra time that you put in, really reduces the bugs, increases the player experience, and
helps the morale of your core team, so it doesn't feel like that you're diving into hell every day. You are trying to get into that code base and fix things, because you know that there's a safety, there's a psychological safety for your developers, and there's a real safety net for everyone in the software team when you have that. Hope
Awesome.
that answers the
Thank you.
question.
Thank you. Okay, I think we can be a little bit cheeky and just squeeze this last one in there. So this one's from Theodore, and it says, how do we avoid writing stubs or mocks for the whole game engine that we use?
Yeah, that's an interesting one. So again, this requires understanding where you want to write stubs and mocks, and that goes back to the question the answer I gave, that you don't want to stub and mock everything. You want to depend upon the engine if it's something that the engine is doing. However, uh, again, yeah, I think it depends on the use case. And you so stubs are things that you write when you just want a class to make happy noises, a functionality to make happy noises. And mocks are things that you write when you want specific answers from them. So if you can use this principle to decide whether you want to write stubs or mocks, or whether you don't want to write either of them because you want to depend on the engine code because they have written their own tests, that is for your own discretion. And also maybe the references that I mentioned have usually helped me understand where you want to do what.
Amazing. Thank you so much, Siddharth, and thank you everybody for joining us today. That's it. We're going to have to wrap up here. But if people have more questions, Siddharth, what's the best way for them to get in touch with you?
I believe Teams is always there, and there's also the code room in the networking. And if there's a lot of things that we can go about, and if there's a bigger group of people, we can just take this talk there and have this chat.
Amazing. Thanks, folks. Enjoy the rest of the day, and thank you again, Siddharth.
Thank you, everyone. Have a good one.